Ladies and gentlemen, welcome to the lecture of the material science. Today is Friday, right? Okay, so on Wednesday we learn secondary bond. I hope you still remember. We start with the dipole interaction. Remember? So first of all, we need to know the definition of the dipole. And then we move to the interaction of the dipole, involving three topics. The first one is dipole-dipole interaction, which we also called permanent dipole bonds. The second one is dipole-induced dipole. And the example is polar molecular with non-polar molecular, right? So it's polar molecular induced dipole bonds. And the third one is induced dipole. We also call this fluctuation induced dipole bonds. Okay, so again, I want to remind you that this might be in your final exam paper. This question might be in your final exam paper. So you need to tell me the definition, and also you need to give me an example. Let me know you understand the dipole interaction. Okay, so in terms of the energy among these three dipole interactions, in the end, I give you example. I give you this PPT, right? So this is the secondary bonding energy. You know, the energy of the permanent dipole bonds, which is dipole-dipole interaction, will be greater than the energy of the polar molecular induced dipole bonds, following by the fluctuating induced dipole bonds. Okay, so this is also important. I want you to remember this. Right, so today we start with a special case of the secondary bond, which is we called hydrogen bond. So hydrogen bonding is that according between the hydrogen and only the most electronegativity elements. So there's a secondary bonding, and especially it's only between the hydrogen and also most electronegativity elements. This is the periodical table on the right-hand side of the periodical table. And then the number here showing you the value of the electronegativity. So you know, when we talk about the most electronegativity elements, that means somewhere around this region, right? Okay. So here is that, so this is the special case, especially for fluorine, oxygen, and nitrogen interact with the hydrogen. So the most electronegativity element means that you have very high AVEE. AVEE, I hope you still remember, AVEE stands for average valence electron density, electron energy, right? So again, it's somewhere around here. So we're talking about fluorine, oxygen, and nitrogen. Why? Because these three elements like electron very, very much. So like fluorine and hydrogen, this electron will be very close to the fluorine. So this will be a very, there's no electron at all. So this is the dipole will be strongly go to this way, right? So you have positive end and negative end. So this is what we call bare proton. Bare proton. Because of bare proton, that means this one has no electron at all, which is very positively charged strongly. right? So in this case, if there's another hydrofluorine surrounding this hydrofluorine, that means this one has a lot of electrons, and this one is a very strong negative charge here. So again, you might think, wow, Professor, this is a case of dipole-dipole interaction. Indeed, this is a dipole-dipole interaction, but because fluorine and hydrogen has a very strong interaction, so that's what we call hydrogen bond or hydrogen bonding. So the bonding between hydrogen and fluorine molecules here is covalent bonds. The hydrogen and fluorine in between these two molecules, this is called hydrogen bond. Okay? So, and we understand lone pairs electrons interact with the bare photon. So the valence electron here is very strong, and then they have interaction. So this is what we call hydrogen bonding. Okay, so AVE here showing you that if you have a high AVE, that means you will have a high electron negativity chi, right? Okay. Right, there's some descriptions about hydrogen bond. The hydrogen bond is a special case for polar molecular bonding. And then it occurs between the molecules in which hydrogen is covalently bound to fluorine, oxygen, and nitrogen. Again, you can replace this to O oxygen, right? Then you will have two hydrogen here, right? O, that will be water. Or you can replace fluorine here to nitrogen. That means you have three hydrogen around here. Okay? So the hydrogen end of the bond is essentially a positively charged bare proton that is unscreened by any electrons. So this proton here is unscreened by any electrons. Right? So this is very, very positively charged. Okay. So the hydrogen bond, this highly positively charged end of the molecules is capable of a strong attraction force, right? Okay, with the negative end of the adjacent molecule as shown here. So the single proton form a bridge between two negative charge atoms. Okay. Right. So because this is a special case for the polar-polar interaction, so the bonding energy must be higher than the normal one, right? So the magnitude of this hydrogen bond is generally greater than that of the other type of the secondary bonds. So this is the most strong bonding energy among the secondary bond. Okay, which is about 0.25 electron volt per molecule. So that's why the boiling point and temperature point of this hydrofluorine and oxygen are abnormally high. You know, if you have bonding energies is high, so it is difficult to take it apart, take these molecules apart. That means it requires higher energy to make this happen. If this system requires higher energy, that means the temperature will be high, right? The temperature is high, that means the boiling point will be high. Okay. So here is the case of the water. So H2O here is that this is a positively charged bare proton here because oxygen and hydrogen and oxygen here. Okay, and this has a very strong electronegativity value. Okay, so and there's non-bonding electron here because it's very high electronegativity. So you have negative N in this region and positive N in this region. So you have a hydrogen bonding. Okay, so these are hydrogen bonds. Right, And of course, you understand the distance between this bond is stronger. Of course, this is a chemical bond, right? Chemical bond, and this is physical bond. So it must be, this H and O must be closer compared to this H and O. So this bond length is longer, right? Compared to 0.101, and this is 0.175. It makes sense to you, right? Okay. Right, so ladies and gentlemen, this is important figures I want you to remember. Hydrogen bonds and melting points. So let's take a look of this line first. This is carbon, right? Silicon, germanium, tin. So this is group 4A in the periodical table, right? With the 4 electrons, with the 4 hydrogens. So as you can see, the boiling point is increasing. Why? Because of what? Tell me. Because the boiling point is related to the permeability. Remember, alpha is permeability, and permeability is related to the number of the electron and the size of the electron, the size of the molecule. Okay, if you have more electrons and the size of your atom is bigger, that means permeability is high. If you have a high probability, that means the melting point, the temperature need to be high for the melting point and the boiling point, because energy required higher to take the molecules apart away from each other. Okay, so if we take a look of the group 14 in the periodical table, that means 4A group. Okay, so this is this is a tetrahedral structure, right? Tetrahedral structure looks like this. Where is that? Okay, it looks like this. Okay, and this is, of course, this is a non-polar molecule. You all understand this. Okay, so if you have a lot of this one, if you regard this as carbon, it can be 4 carbon will be methane, right? Methane. And if you replace this from carbon to silicon, this one will become silane, right? SiH4. Okay, and we are talking about the interaction between these. Okay, between this one. So if you have a bigger molecular size, that means this silicon is bigger than carbon, of course. Then what? Then you have more electron numbers. Why? Because you have screen effect, right? Okay, and the probability will be high. Probability high is that if you have a bigger size, this bond will be what? Will be stronger. Bonding will be stronger, and then dipole interaction will be stronger. And that's why it requires higher energy to take these two apart. If you require high energy to take these two apart, then the temperature will be high, right? Temperature is a representation of the thermal energy. Okay, so this is the reason. So the temperature, the boiling point will increase. Okay, if you take a look of the group 15, which is a polar molecule, this is, you replace this nitrogen and then phosphorus. Of course you have PH3, NH3, and HBr, right? Sorry, arsenide, nitride. Okay, ASH3, something like this. And as you can see, again, we take another way around. So if a molecular size is small, getting smaller, right? SB, AS, and P getting small, right? So the size is small. And then what? And the probability will be small. If the probability is small, the dipole interaction will be less, will be decreased. If a dipole interaction decrease, that means what? The van der Waals bond decrease, and then the boiling point decrease. It's the same thing when we talk about increasing and decreasing. But you might say, why, Professor? Why? If you think in this way, if you use this probability to think of boiling point in this way, but why nitrogen is here? The ammonium is here. And why HF is here? Why H2O is here? It should be decreased, right? But why these three here? Because of the what? Because the hydrogen bond. Because their bonding is stronger than others. So it requires higher energy to take oxygen molecules away from each other. And if it requires higher thermal energy, that means the boiling point will be high. The melting point will be high. Okay? Are you with me so far? Yes? Okay, good. So the van der Waals force against the hydrogen bondings, the differences, there's no differences. Hydrogen bond is a special case of the van der Waals force, or van der Waals bonds. Okay? It's just a special case. But you might say, well, Professor, how about this if I change this to, for example, ammonium? That means N here, and then there's 3 oxygen here. Of course, this has also the hydrogen bond. Right? It doesn't matter you replace this to another chemicals, if this is oxygen or nitrogen. Right. So we are going to be the end of the chapter 2 soon. So now let me introduce you the properties of the bonding. The properties of the properties from the bonding means that you know, when we talk about energy, just now we are talking about melting point and boiling point, which is related to the secondary bonding energy. How about others? So this is a melting point temperature, right? When we talk about melting point temperature, that means it's cohesive forces against the destructive forces. Cohesive forces is a secondary bond. Destructive forces is thermal energy, right? So, and also this is bond length. If we think of the bond length, which is R, it can be big, it can be long, it can be short. So when we have a bonding energy, remember there are 2 atom interactions we draw in this way. So this is the bonding energy, and R0 is what? Equilibrium spacing. I hope you still remember this was in your midterm exam paper. Okay, so if you have something like this, which you represent 2 curves, what does this tell you? The energy between 2 electrons or 2 molecules is small. This one is smaller than this one, right? So the melting point, MT, this has a larger melting point. This has a shorter melting point. If you regard this as 2 atoms, right? Atoms, one here and another one here. So this is a smaller melting point. So if I show you a Kahoot on next week, and then I want to ask you please rank the melting point of 3 curves. I'm sure you can tell me, right? Right. If the melting point temperature is larger, if the bonding energy is larger, then you got higher melting point. Okay, this is one of the melting point related to the bonding energy. How about another one? Alpha. Alpha is not the probability here. It's a coefficient of the thermal expansion, which is like this one. You know, when you hit a solid materials, when you increase the temperature surrounding these materials in the environment, this material will expand 3-dimensionally, right? From x-axis, y-axis, and z-axis. Okay, but here we just think of the 1 dimension only. Delta L is here, and then divided by original length. It will be equal to the alpha times the T2 minus T1. T represent the temperature. So if you increase the temperature, and this will be longer. Okay, increase here, and delta L will increase. And it depends on different materials. You have an alpha, which is a coefficient of thermal expansion. And the thermal expansion is related to the what? With the energy. Why? Because as you can see, if you expand the materials, that means the distance between atoms will be away from each other. That means what? That means, again, the cohesive bonding energy against thermal energy, against the disruptive energy, right? So again, if I show you these two curves, and I have these two energies, which one has a higher alpha? This one, right? Why? Because the energy required is small. So alpha will be high. So large alpha and small alpha. Right? Piece of cake. Right? No. Yes. Or it's not a piece of cake. No? Right. So alpha is larger if the energy is smaller. Okay. Right. This is bonding energy against the melting point here. Just that you know that, covalent bond, magnetic bond, something like this. Right. Finally, I want to show you this important table. This is the primary bonding involving ionic bond, covalent bond, and magnetic bond. And this is secondary bondings. Basically, is van der Waals bonds, and the special case is hydrogen bonds. So here is that, as if there's 1, 2, 3, 4 here. If I want to ask you, please let me know which one is the directional bonding among these 4. So can you tell me? Directional bonding is covalent bond and the van der Waals bond, right? Non-directional is ionic bond and magnetic bond. Right. So, and this is elements, example of the elements we're showing you here, and stable configuration, molecules here, and the bonding energy. Bonding energy for the ionic bond is between 3 electron volt to 8 electron volt. And for the covalent bond is about 7, you can have a very large 7.4 electron volt and very small. Again, for the magnetic bonds. Okay. However, if you understand the bonding energy here, you must need to know that the secondary bond, the bonding energy is much smaller than chemical bond, because this is physical bond, right? So generally for the van der Waals bond, the energy will be 0.1 electron volt. But however, for the hydrogen bond is a special case of the covalent van der Waals bond, right? So the energy is higher, which is about 0.52 electron volt compared to here, 0.1. Okay? Okay, good. Water is a very interesting molecule because water has a hydrogen bond. And I want to show you that there's a very interesting polarity of the water, and the one telling you that the differences between the polar molecules and non-polar molecules. The one they use is electrostatics. Electrostatics is the one you just collect some charges by kind of what we call that electrofriction here. So you can get positive charge, you can get negative charge, depends on the material you use. Okay, so this is a kind of so this is a kind of, you can get charges to the materials. And one of the interesting things here is that this is called triple electrical effect. You can use this as a kind of narrow generator to generate power, but the power is very small. Okay, because this is attraction and repulsion force. So you just do the electrical friction, and you can get the power for this, and that's why we call it a nano generator. Okay, this is a very interesting study, just for your information. Right, and the chapter 2.8 molecules, we already talked about this in previous lectures. So here I will just skip this chapter, this section. Okay? Right, so that's it for the chapter 2. It's been a long time we introduced you because this is very important topic. You need to understand molecules. You need to understand atoms first. And atom has a nucleus and electrons surrounding the nucleus, right? So one of the important things is you need to understand the electrons. Okay, and then after that we understand the interactions between atoms so that it becomes molecular. And we need to know the bondings, and bonding involves primary bonding and secondary bonding. And so now you know everything about the molecules, and now we are going to move to the crystal. Crystal means what? You have 1 mole of the atoms together, and it becomes a huge you have thousands and thousands of atoms together. So we regard this as a solid. You can see by your eye. Okay, so this is the topic we want to know. Right. So I think before that, it might be a good idea to have Kahoot first. Okay, before we move to the top chapter 3. To talk about the crystal, that means you will have 1 mole of the molecules or atoms get together, and it becomes a solid. So and somehow if you pack the atoms very well in a very good order, that means in that case we call it crystalline solid. Crystalline solid. So first of all, we need to understand what is crystal. And if you have a crystal, you need to address the crystallographic point, direction, and plane. Point is 0 dimension, right? Direction is 1 dimension. Plane is 2 dimension. Okay, so you need to address what is that plane, what is that direction, where is the point. And after that, we're going to talk about non-crystalline materials. So this is a crystal. This is a crystal. But when I tell you this is crystal, do you believe me? Well, I'm a professor. You better believe me, right? But if you are in a shop or if you are on the street and they show you that, well, hey, buddy, this is a crystal. Do you believe him or her? No, you don't. Right? This might be a plastic. It's not a jewelry. It's not a very expensive crystal jewelry, right? Why? And how are you going to define? Is this a good? Is this the good or a fake jewelry? One of the very good tool to identify the jewelry or not is if you have something like this diamond, you have X-ray beams. The X-ray beams pass through this crystal, and if the pattern, if this X-ray pass through this diamond or this material and show you a pattern something like this, which is a dot-like pattern, yes, this is a crystal. And yes, this might be a very expensive material, like jewelry, like diamond. If the beam come in, pass through it with a nothing and a dark image, you might say, wow, this guy is not a good guy. He want to give you something which is fake. Okay, and this tool we call X-ray, and this phenomena we call X-ray diffraction. And X-ray diffraction can identify this is a crystal or this is not a crystal. Okay, not only X-ray but electron beams. If you have electron beam, of course, electron beam can be produced in only in the vacuum situation, vacuum environment. If electron beam pass through this diamond, through this diamond and give you a pattern like this, you will be happy because you got a really good material. Okay, it's not plastic. Plastic doesn't show you the pattern like this. Okay, so this is a gallium arsenide, which is GaAs. This is gallium arsenide, as gallium arsenide crystal. And TEM, you don't need to worry about this now. You just know that I have an electron beam and pass through this, and I get this pattern. Okay, so the brightness spot near the center is produced by the incident electron beams, which is a parallel to 110 crystallographic direction. Okay, what does this mean, 110? You know, I just told you that all the crystals, you can address the crystal by 0-dimension point, 1-dimensional direction, and 2-dimensional planes. Okay, and then if your electron beam or if your X-ray beam shoot from left to the right in this direction, and you put this diamond in different position like this, or this, and it will show you the different pattern. So when you see the different pattern and you go and check your database, you will realize this pattern will belong to this direction or another direction, or this plane or another plane. For example, if this plane, if you shoot on this direction might be 110. It might be 110 plane in this plane. However, this plane will be 010, for example. So you, according to the different pattern, you can identify the different planes, and also what is these materials by these angles, by the distance. This is very interesting, right? Are you excited about this topic? No? Oh, yes? Oh, excellent, excellent. I'm happy for you. Okay, each of the other white spots result from the electron beams that is deflected by a specific set of the graphic planes. So you can have different direction, you can have different planes. Okay, but this is a long story. I will leave this for the next weeks or next weeks. But let's start from the introduction. So the crystal structure we have 3.2 is the fundamental concepts. So first of all, let's define what is crystal, what is non-crystal. Non-crystal, sometimes we call amorphous material, or it can be called non-crystalline material. So what is crystal? If you take a look of these two structures, I'm sure you understand very quickly. This is the crystal structure. This is a non-crystal structure. Why? Because this pack very well in order. This doesn't pack well, and there's some space between the atoms. So you cannot find an older way to get this, to have this, to define this is a crystal structure. So for the crystalline material, is that atoms are situated in a repeating or periodical array over a large atomic distance in a repetitive 3-dimensional patterns. 3-dimensional means what? X-axis, X-axis, Y-axis, and Z-axis. They are all repeat in a long distance. Right. So what is crystal structure? For example, this is one type of crystal structure. If you put this unit cell into this one, and you pack this in 3 dimension, X, Y, Z direction, then you can get these crystals, the crystal like this. So there is extremely large numbers of the different crystal structures. So the description of the crystalline structure, you can use different way. So the first way is atomic hard sphere model. This is called atomic hard sphere model. Okay, you have a ray atom here, and you pack this in a very good order and very close. And another one is called reduced sphere unit cell. This is called reduced unit because you reduce, so you can see something behind this in the layer 3 and layer 2 and layer 3. So you reduce the atom so you can see it clearly. So this is what we call the reduced sphere unit cell. Another term is lattice. Lattice. What is lattice? Use a context of the crystal structure. Is that this is lattice distance. So three-dimensional arrays of the points coinciding with the alternate positions. Okay, so this is what we call lattice. Okay. Right. So one of example to show you here is this is called hard sphere model, right? Hard sphere unit cell. This is a hard sphere unit cell. This is a reduced sphere unit cell. Okay? And if you put this unit cell together in three-dimensional direction, and this is called aggregate of the many atoms by hard sphere unit cell, right? Of course, this is a face center cubic crystal structure. We are going to introduce you this very soon later. So again, when we talk about crystal and non-crystal, we can think of we can use energy to think of this. Right, so this is one atom here and one atom here, and then when it's decrease the distance, you can get an energy curve like this with the distance, right? Of course, you understand this is called equilibrium spacing and the bounding energy. Okay, but for the non-dense random pack, what does that mean? Non-dense random packing. That means the energy, the energy between two atoms will be averagely what? Low. Right? Will be averagely low. So it might be somewhere around here. It's not reached to the lowest energy state, which is the most stable state. So this might be the typical neighbor bound length and energy, because it's long, right? It's long, average. But for the dense older packs, the energy will be here, very, very low, very stable, and distance reach to a equilibrium spacing. Okay, easy. So this is a structure of the crystalline SiO2. What do you know? What's crystalline SiO2? Quartz. 石英. Okay, in Chinese is 石英, right? So quartz is made of silicon and oxygen. So you have like this, and you know the unit cell is something like this. You can repeat and repeat like this. Okay, so atoms stacked in a periodical three-dimensional arrays. So it can be a typical of the metal, ceramics, and polymers. Some polymers. And this is another example, which is non-crystal materials. It packed like this. This is oxygen, this is silicon, and packed like this. And you cannot find anything in order. And what is this? Non-crystalline SiO2. Glass. Body. Okay, this is quartz. This is glass. Okay, made of SiO2, but different structure give you the different properties. Okay, atom has no periodical packing, and they occur from the complex structures and rapid coolings. You don't understand this? Don't worry, we are going to show you soon. And also, we can call non-crystalline, or sometimes called amorphous. Okay. Right. So now let's move to the section 3.3, unit cell. Unit cell is a very important thing to define. This is a crystal, or this is not a crystal material. So unit cell, what is the definition of unit cell? Unit cell is the crystal structures is subdivided into a small repeating entity, which is the smallest repeating entities. So based on this unit cell, you start to increase 1 unit cell, 2 unit cell, 10 unit cell, 1 moles of the unit cell, and you just pack it, and you become crystal. So for the most crystal structures, cells are parallel peptide, okay, or prisms, have the 3 set of the parallel faces. So three set of the parallel faces is, if you take a look at this is a cubic structure, right? Cubic structure. And yeah, how many faces here? 1, 2, 3, right? And for here is another one is number 4, right? And numbers 5 and number 6. So there are 6 faces. Okay, so 6 faces means what? 3 sets, right? 3 sets. XY plane, XZ plane, and X, what's this? Also, YZ plane, right? YZ plane. 3 sets. So the base structures unit, this is the base structure unit, okay? So convince usually detected that the power corners, this one, coincide with the centers of the hard sphere atoms. Don't worry about this. And then more than a single cell may be chosen for a particular crystal structure. So for the crystal structure, it can have more than one single cells. It depends on the definitions. So I'm going to show you here. For example, you can use this as a unit cell. You can use this, as you can see, this can repeat, right? From the left, from the right, from the top, from the bottom, from the front, from the back. So this can be repeat. This can be repeat. This can be repeat. How about this one? This can be repeated, right? But is this unit cell? Is this the smallest unit cell? I should say, is this the smallest repeating unit? No, this is not. This is not. Actually, this is the smallest repeated unit. Is this the small? Can this repeat? No, pentagon doesn't work. Pentagon is not a repeat. Is not a repeated unit. You cannot make this to 3 dimension. No. Okay. So here is the example. Is this is a 2-dimensional repeat unit, right? And this is 2-dimensional repeat unit. How about this one? Can you tell me where is the repeat unit? Okay, how about this one? This might be in your final exam paper or Kahoot next week, right? Okay, so please think of this. It's not difficult if you just try to see where is the repeated place, and you can find out repeated unit. Okay, for example, is eyes here, eyes here. You know, wow, something repeated here. You might have a dot here, and then see that, well, this can be a repeated unit. As I just told you, this can be a repeated unit, but this is not. Right? Okay, so where is the repeated unit? Repeating unit, please tell me. How about this one? You know, pentagon doesn't work because if you put this together, this is not a 2-dimensional repeated unit, so it doesn't work. Okay, you have space here, right? Okay, so let's go to the section 3.4, metallic crystal structures. So basically, repeat unit, 2-dimensional repeat unit or unit cell is very important to identify whether this is a crystal structure. So metallic crystal structure, I think you have learned this when you are in high school. So I think it's not difficult at all. So we understand metallic bonding is a non-directional bonding, right? So the type of the crystal structure for the most of the common set metals. So you might say, why, Professor, why we need to start to learn crystal structure by using metals? Because metal, you only have one type of the atom. It's easier. It's the most easy topic to start with. If you use ceramic crystal structure, that will be complicated because the ceramic might involve 2 types of atoms or 3 types of atoms, even 4 types of atoms. So you make the structure more complicated. So metallic crystal structure is the most easy way you can start to learn the crystal structure. So there are 4 types of the crystal structure. Okay, the first one is called simple cubic structure. The second one, face center cubic structure. We use FCC for short. And the third one is body center cubic structure, BCC. And the fourth one will be hexagonal close pack structure, HCP. I want you to remember this well, and it's easy actually. Okay, so for this case, we only talk about, normally we talk about cubic geometry. Cubic means what? The length of the x-axis is equal to the length of the y is equal to the length of the z-axis. Right? That's why we call cubic geometry. Right. First one, simple cubic structure, SC. So what is simple cubic? Simple cubic is what? If you have 8 corners in your cubic cell, in your cubic cube, in the cube, right? You have 8 corners. So one corner will have 1 atom. This is a simple cubic structure. So, and this is reduced model. This is a sphere model, right? Sphere, half sphere model. This is reduced sphere model. Okay, and this is not a unit cell. This is a unit cell, right? Because you can use this unit cell to repeat. Okay, so there's something I want you to know. Close pack directions are cubic edge. You don't need to worry about close pack. Close pack means that between this, there's less space. This is what we call close pack. But I'm going to talk about this later, so don't worry. So the first term we need to know is coordination number. What does that mean, coordination number? If you have 1 atom, how many atoms touch this atom? That's what we call coordination number. Okay, so this is a unit cell here, unit cell. Okay, and you have 8 unit cells in this cube. So let's point this one, the red atoms in the center, and how many atoms touch this atom, and the numbers of the touched atom is called coordination number. So use your imagination. Let's point this sphere, this atom here. So how many atoms touch this one? 1, in this case 1, 2, 3, 4, right? 1, 2, 3. This 3 doesn't touch. This 3 don't touch this one, right? So 1, 2, 3, 4. How about any more? Yes, the one in the front. I didn't draw it, right? So this is 5 and 6. So you have 1, 2, 3, 4, 5, 6. So coordination number is what? The coordination number is nearest neighbors. Equal to 6. You might say, wow, Professor, why I need to learn this? What does that mean? Oh, is that so important? Yes, this is very important. Why? Because this one represents what? Bonding, bonds. The bonds means energy. You have, and then if you want to take this apart, it requires 6 times of the bonding energy, right? Okay, so if you have more coordination number, that means what? The bonding will be strong. The energy required higher to take this apart. Okay, so the second term we call atomic packing factor. What does that mean? Ladies and gentlemen, I want you to remember this very well because this definitely will be in your final exam paper. Okay, atomic packing factor is that the value of the atom in a unit cell divided by what? The value of the unit cell. It means what? It means how many space in this unit cell or how many solid materials in this unit cell. The more you have, the more solid material you have in this, it means what? It's more dense, right? You might say, well, Professor, why don't we just use density to represent this? That's another story, but please remember this first. So please tell me, this is called simple cubic, right? Simple cubic structure. Please tell me APF. The value of the atom unique cell, value of atom here. So how many? So the value of atoms, remember atoms, right? In unit cell, how many atoms in this unit cell? How many? 1, right? 1 atoms. Why? Because this is 1 ace, 1 ace, 1 ace, 1 ace. So you have 8 1 ace. That means you have 1 ace times 8. That means 1 atoms, right? And do you know the value of this one? Yes, you do. Why? Because this is R, right? This is R. And 2R is the length of the cube. So this, for example, this is A. This is half A, right? So what can you do this for me? So R is 0.5A. So close back direction. Don't worry about this. Close back direction now. And you have 1 atoms per unit cell. And then that's why you have 1 here. And you need to calculate the value of the atoms. What are atoms? Please don't tell me you don't know. Okay, if you don't know, you go to high school. No, you go to junior high school. Okay, so this is 4 out of 3, 4 thirds times pi, and you have the radius the radius times power 3, right? So radius means 0.5 m, 0.5 a. A is the length of the cube. Okay, and then you have what? You have a power 3 here, because this is the value of the unit. As a result, you got 0.52. This is kind of ratio, right? Because this is value divided by value. That means there is no unit. And 0.52 means what? They are 50%. There are 48% empty space in this cube. So the packing is what? The packing is not good. It's not a good packing because it's about half of the space is empty in this cube. So it will be very losing structure, right? So only 50% packed with the solid materials in this structure. Okay? So APF for a simple cubic structure is 0.52. So as I told you that there are many empty space in this structure. So you cannot find, this is not, it cannot be formed because it's too losing. So the simple cubic structure you can only find in this one. This is the one. Polonium. Okay, rare due to the low packing density, 0.52, too low. It's not going to happen. It's not a stable structure. Right. So let's take a look at the body center cubic crystal structure. The body center cubic crystal structure is looks like this. This is a unit cell. And this is a half sphere model. Of course, this is not a unit cell, okay? And of course, this is a reduced sphere model. Right? Reduced sphere model. Okay? Right. You might say, well, Professor, why this is different color? It doesn't matter. It's just let you know. It's the same thing, but just let you know there's one in the center. Again, please tell me. So that definition is the cubic unit cell with the atoms located at all 8 corners. So body center means what? You have 1/8 of the atoms located in the corner, 8 corners. However, you have one single atom in the center, and this is what we call body center cubic crystal. Okay? I'm sure you learned this. Right, so at this moment, you need to tell me that the relationship between the radius and the length of the edge. Okay. So, how many atoms in this? How many atoms per unit cubes? How many atoms? As I told you that you have one ace, right? One ace atoms located in the 8 corners. So 1 ace times 8, that means 1 electrons. 1 atoms. 1 atom, right? And you have 1 in the center, that means you have 2 atoms. Okay? How about the relationship between the radius and the edge, the length of the cube edge? Okay, so let me tell you that this is R, right? This is R. And this is what? This is 4R. If you put it 3-dimensional, it becomes 2-dimensional. This is 4R, right? 4R equal to root 3A. Why? Because this A here, this is root 2A. And of course, this is root 3A. Right? No problem. So as a result, you know this is 4R. So you can have the relationship between radius and the length of the edge. Okay? So A equal to 4R divided by root 3. Right, so please tell me the coordination number of the BCC. Very easy, right? Tell me. 8. Am I right? Am I wrong? Am I right? Am I wrong? I'm right, right? Right. Good. If you don't understand this, please go to junior high school. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Right? 8 in the back. So, and you know, the relationship between the radius and the edge is like this. So, do you know the APF? APF? Please tell me APF. APF is what? How many atoms, how many volumes occupy in this unit of the spheres occupy in this space? Right? So you have 2 atoms, right? 2 atoms in this unit cell. And again, you know that this is the value of the one single sphere. R3. So you have R3, R power 3, right? It replaces to this one. So you know this. And again, this is A power 3. So as a result, if you do a simple calculation, that will be 0.68. That means 68% of the in the 60% of the space was occupied by the solid material. There are 32% empty space in this unit cell. Okay? Right. So it's 0.68. So what kind of materials has this BCC structure? The chromium, moly, and tungsten ions, which mainly in the periodic table in the 16156. So it's like this. 6156 chromium. This. Okay? And again, you don't need to remember this. You don't need to remember these elements, but you need to know what's BCC. Okay, so it's in the periodical table, group 1, group 5, and group 6 mainly. Right, the third one is face-centered cubic crystal structure. So this is face-centered cubic crystal structure. Why this called face-centered? because I told you there are 6 faces, right? 3 pairs of the faces, right? So and all the atoms face the face. Okay. Okay. One is noun, one is verb. Okay. So all the atoms face to the face, and ahead to the face. You should say that in that way. So if you have a single unit, it looks like this, and then this is again, it looks like this, and this is reduced spheres. You can understand that there's one atoms behind the face. You can see. Okay, so this one is special. If you take a look from this direction, this is 1, right? Okay, this is 1, 2, 3, 4, 5. The layer 1 has 1. Layer 2 has 1, 2, 3, 4, 5, 6. It's 1, 2, 3, 4, 5, 6. This is layer 2. Layer 3 will be like this. So it depends on which direction you look at this crystal. It shows you different geometry. It shows you different geometry, a different way to look at this, different things. Okay, so face-centered cubic structure. First of all, the atoms locate at each of the corners. There are 8 corners, right? Again, you locate it in 8 corners, and another 6 atoms face to the 6 faces, the centers of all the cubic faces. Okay, this is center of the sphere, right? So this centers of all the cubic faces. So please tell me how many atoms in this unit cell. Can you tell me how many atoms? 1, 2. You have 1 ace, right? Again, you have 1. And how many? This is half of the atoms, right? Half of the atoms. So how many atoms in this unit cell? You have 6 faces, remember? And each faces has a 1/2. You have half of the atoms. Though there are 6 faces, so you have 3 atoms. And 3 atoms plus the 1 atom which is located in 8 corners, right? So there are 4 whole atoms may be assigned to a given unit cell. No problem. Okay? So 4. Okay? Again, and then in order to know the age, the cube age and length, you need to, in order to know APF, you need to know the age, length, and the atomic radius, right? The cube age length. So look, this is cube age length A, and this is 4R. Remember? So you can have a relationship between these. So please tell me, this is junior high level. A power 2 plus A power 2 equal to what? 4R power 2. So you know the relationship between radius and the cube age length. And you understand A equal to 2R root 2. Right. So please tell me the coordination number. This is a little bit, you need to use your imagination a little bit. Because in order, so for the metals, each atom has the same numbers of the nearest neighbors and the touch atoms, which is the coordination number, as I just told you. This is related to the energy, right? So for FCC, how many? The coordinate, I had you. Okay, so y is 12. Y is 12. If you point out this one, this is the one you want to count. So it's 1, 2, 3, 4, right? 1, 2, 3, 4 is 1. And then this half atom in the back, 5, 6, 7, 8. The atom on this side has a 5, 6, 7, 8. And the atom on the front side, this is the back side, from the front side, has another 4. Right? So 9, another next one, 9, 10, right? 11, 12. Okay, so you have 4 plus 8. Are you with me? 1, 2, 3, 4, right? And then this one, 5, 6, 7, 8. Right? You can see that, but of course you cannot. This is one behind, so you cannot see. 5, 6, 7, 8. And then in the front. Okay. 9, 10, 11, 12. Or you can use this 1, 2, 3, 4, right? 5, 6, 7, 8. And another 4 in the front. That will be coordination number 12. Okay? So now, important thing is atomic packing factor. Tell me. Once you know the relationship between the radius, the atomic radius and the edge length, right? So you can write down this for me. So I don't want to waste your time. You have 4 atoms. Remember, you have 4 atoms. And then after you do the calculation, the number is 0.74. So there are 40% of the unit cell occupied by solid material. Right. So this APF is 0.52, 0.68, 0.74. Which one is the most close pack? So 0.74 among these 3 is the maximum packing possible. So mainly this one is more popular among the elements. Okay? Right, so I think I run out of our time today. Please read this by yourself. Let me finish. I think we don't. Right.